So the second assumption is plane section remain plane after bending, and strain is proportional to strain in the concrete, and reinforcement shall be assumed proportional to the distance from neutral axis. This I can explain in this picture that if this was the section plane before bending, after bending it will remain plane, and with distance from the neutral axis the strains are linearly increasing and they are proportional to the distance from the neutral axis. And it is further stated that strain in the reinforcement is equal to the strain in the concrete at same level. So in this picture, if steel is present over here on the tension side, so the strain in the steel bars and the concrete surrounding it will have the same strain. So strain is actually proportional to the distance from the neutral axis, and whether it is the concrete or steel at that place, both will get the same strain magnitude. So I can also rewrite it like this, that epsilon C strain in the concrete, epsilon stand we use a Greek letter for strain with subscript C. Epsilon C is equal to epsilon S. Both are equal. S for steel. And stresses in the concrete and steel can be computed from the strains by using stress strain curves for concrete and steel. This is understandable that you have the stress strain curves for both materials. So if in experiment you are recording the strains, corresponding to the strain you can measure the stress from the stress strain curve. If you have the strain, you can measure the stress. So in experiment, if you just recorded the strains and you know the stress strain curves, so from strains you can get the corresponding stress. Furthermore, as per ACI provision 22.2.2.1, failure strain in concrete at the extreme compression fiber shall be assumed 0.003. So it means at the ultimate crushing stage, which we stated that it is actually 85% of the peak, 0.85 FC prime. So corresponding to that, ultimate strain fixed by ACI is 0.003. Almost for all concrete grades, normal strength concrete grades. But in actual, you may find while doing testing that in some concretes it may even approach 0.006 or bigger. But ACI has fixed a conservative value of 0.003 to develop the equilibrium equations. Tensile strength of concrete shall be neglected. As I said earlier, it is very less, so we are going to ignore it. The relationship between concrete compressive stress and strain shall be represented by a rectangular, trapezoidal, parabolic, or other shape that results in prediction of strength in substantial agreement with comprehensive tests. This is actually one permission given by ACI, that instead of actual stress strain, you can replace it with the equivalent stress strain of shapes rectangular or trapezoidal or parabolic or any other, if the prediction is in good agreement with the actual and you have in your support comprehensive test results. Now again, we want to take into discussion this stress strain curve of concrete. And as we have seen different assumptions of ACI, so this is the peak compressive strength. We call it compressive strength or peak strength or maximum strength. And corresponding to this, in normal concretes, strain will be around 0.002 to 0.0025, corresponding to peak. And ultimate, as I earlier mentioned, that ACI has fixed this ultimate strain corresponding to 85% of peak as 0.003. Now in ultimate strain design, we actually want to calculate the resultant compressive force C. And we know the stress strain relationship of the concrete. So first step is we want to calculate area under the curve, and then that area under the curve multiplied with the cross-sectional area on which it is present can give me the resultant C force, compressive force. Since the stress strain curve is parabolic, so we need to do integration. If we know the equation of this curve, we need to do integration to calculate area under the curve. And then multiply that area with the cross-section on which these parabolic stress strain relationship is present will give me the resultant C force. If the stress strain relationship is linear, we will get a triangular area, as you have seen for homogeneous elastic beams or the concrete in very initial range subjected to very low level of stresses. But in ultimate strain design, since we will load the specimens cross sections to their maximum limit, to their crushing stage, so we will get nonlinear stress strain range, and so we need to determine the area under that parabolic curve. So there is one simplified approach given here, which will be valid up to certain range of FC prime, which we want to discuss, which will be used in the next slides. For example, for this picture, if you state that this area, this curve is valid for all concretes up to 30 megapascal, ranging from 17 up to 30 megapascal, because less than 17 or 17.5 megapascal is not permitted by ACI as structural grade concrete. So you need to have the strength above 17.5, and preferably in Pakistan we use 20 megapascal strength in normal public sector projects, minimum required. So F up to 30 megapascal concrete, if this is the stress strain curve, and if you can calculate area under this curve exactly by doing integration or If by you have this experimental curve, you can use planimeter, or on a graph paper, if you will count the boxes under the curve, you can get the area either by doing integration or otherwise. Then divide that area under the curve with the abscissa, which is the ACI proposed ultimate strain, which is 0.003. Once you will divide this area with this, you will get the answer as F average. So it means the actual area which is shown under the curve, let me show it with hatched line. So I may say that all this area under the curve if I will divide this with 0.003, it will give me F average, which will be equal to this dotted line. So it means I have converted this area into a uniform, a varying stress into a uniform average stress, F average, by making both areas equal by dividing the area under the curve with the abscissa. F average multiplied by 0.003 will still give me area under the curve. So for concretes up to 30 megapascal, it is well established that this value will be around 72% of FC prime. 1 o'clock. It will be up to 72% of FC prime for all concretes up to 30 megapascal. So now, if I have for concretes up to 30 megapascal this F average, I can get a very useful unitless ratio represented with a Greek letter beta with subscript 1, which is the ratio of average strength over crushing strength, which we have selected as 85% of peak. So it means for concretes up to 30 megapascal, we will end up with beta 1 equal to 0.85. So for all concretes up to 30 megapascal, this ratio of average over crushing will be 0.85. So this beta 1 we are going to use in next slides, where we want to replace the actual stress strain curve with the uniform stress block depth. This slide is very important, where the entire flow chart is summarized, at how we will get the internal capacity of a section in ultimate stand design. Imagine that this is a beam of cross-sectional width B, total height H, and its reinforcement distance from the compression face, named as effective depth D, is also marked. Imagine that this beam is simply supported, subjected to a uniformly distributed load, and we are actually working on the mid-span section, which is under maximum stress. So this section which is shown here is the section at the mid-span. And at the moment, in this cross-section, neutral axis is at this position, shown with the dotted line. So above that neutral axis, there is a compression, and concrete is contributing in that compression force. And below neutral axis, there is a tension, and concrete role is negligible and it is not considered, and all the tension is being developed by the steel bars. So Cc is given by the concrete and T is given by the steel. As ACI has fixed that the ultimate strain, crushing strain, which will be the strain in the extreme fiber of the cross section from neutral axis, and its value fixed is 0.003. So once this top fiber will approach 0.003, and corresponding to that the neutral axis depth C and the strain in the steel bars at that stage when concrete approach its crushing is very important. And since we have discussed in the assumptions, plane section remain plane and strains are linearly increasing, so the strain diagram linearly increasing from neutral axis, so its magnitude is like this, linearly increasing, and below neutral axis it is like this. Since below neutral axis we are not interested in in using the less magnitude or less capacity of concrete in tension, so we are only considering the tensile strength of the steel bars. So we are more interested in knowing what is the strain magnitude at the level of the steel layer and the extreme fiber compression strain, and corresponding to them where is the neutral axis C. So in testing, if we know this strain diagram, we can solve the complete problem, because from strain diagram, as we mentioned in the assumptions, we know the stress strain of the materials. From strain I can draw the stress, as in this picture above neutral axis. This is the strain diagram, and for concrete I know the stress strain curve, so that is why from this strain diagram I can plot this stress diagram. Since the top fiber is at 0.003, so it means top fiber is over here and it approached 85% of the peak, and one layer which is at FC prime, which is little inward from the top at that stage, is over here. And since on the tension side concrete is neglected, so all the steel bars are concentrated at this position, and since steel is linear elastic, it obeys Hooke's law, we can multiply the strain with modes of elasticity to get Fs. It is shown over here. So the concrete stresses are shown with reference to the layers fiber by fiber above neutral axis, and their corresponding magnitudes are shown, which is just like the stress strain curve of concrete. While in steel, all the bars are concentrated in one layer and they are being strained to a magnitude epsilon s multiplied with modes of elasticity will give me Fs. So this is the actual stress profile above neutral axis in material concrete. If I can replace this with a simplified uniform stress block with the condition that from both pictures I will get same amount of Cc, and from both pictures I will get same amount of the point of application of the resultant Cc. If both I can prove, then this simplified right side picture will be more preferred, because it is much easier to calculate Cc from this, because I just need to multiply the uniform stress 0.8 Fc prime with the width of the cross section B and the depth of this uniform stress block A, and the answer Cc which I get, if it is equal to the value of Cc which I will get by integrating this area under the curve, by doing integration on this curve and getting the area and then its point of application, will be little more tedious than calculating it by this uniform stress block. But then I need to prove that both pictures will give me same answer. Once I get the stresses, I will multiply them with the area on which they are present. I will get the force. So stress in steel multiply area of steel will give me T. Stress in concrete multiplied by area will give me Cc. And in this way, I can get their point of application, and the lever arm in between them I can calculate, and then Cc equal to T, Cc equal to lever into lever arm, or T into lever arm can give me internal capacity. So I started from strain diagram, from strain the stress, from stress the force, and from force, knowing the internal lever arm between them, I can calculate the internal resistance. So it means M internal resistance will be equal to either Cc into lever arm or T into lever arm. Now the question is, can I prove that Cc from this picture and this equivalent picture both are equal, and as well as their point of applications, A by 2 is equal to beta C, and C actual neutral axis depth, is it equal to A over beta 1? So if I can prove that both pictures are equal, not only in terms of magnitude of C, but also in terms of point of application, then everyone will accept this simplified approach. So Whitney was the researcher who actually proposed this uniform stress block depth. And one other picture which again highlights the same story, that if I can make them equal, actual versus equivalent, and on this isometric view, then I will get point of application along with the force magnitude of C and T, and knowing their internal lever arm, I can get the internal capacity. So rather than working on actual, I can replace it with this uniform stress block, and with less effort I can calculate the answer with same accuracy. This is what is proved here on this slide. So the last slide of today's lecture, but I recommend you to watch the video and prepare yourself for the entire 2-hour lecture delivered with section B. So in next lecture I will discuss the example, and you need to solve that example at home, which I have assigned to section B, because the recorded lecture is uploaded in your files folder and you are recommended to watch that video. So what I have done up till now is just repetition of same lecture with your section. Now I want to prove that both are equal. That I can prove if I will say this CC is equal to this CC, and this A by 2 is equal to this beta C. So their point of application and as well as magnitude is same. So on the previous slide, we have proved that up to 30 megapascal concrete, F average will be 0.72 FC prime if we divide the area under the curve with 0.003. So that F average is applied on a cross section of B into depth C. So this is actual. Actual condition is I got the area under the curve, although I converted it to F average, but it is actual because I just calculated that area under the curve exactly and divided with the abscissa, I got ordinate, and this average stress I multiply with the actual area on which that average stress will be present. So left hand side is actual, and right hand side is Whitney's proposed, that 85% of FC prime uniform stress if it is present on a cross section which has a width B and a constant depth A, which is shallower than C. If both are made equal, I will keep B and B will cancel, and I will keep A on one side, and rest variables I will bring on the other side. It is interesting to note that I got this ratio, and up to 30 megapascal concrete, this answer is 0.85. And actually we have used the Greek letter beta 1 to represent that. So it means this, we got this powerful relationship that both pictures are equal when A is equal to beta 1C, and beta 1 will be 0.85 up to 30 megapascal concrete. However, for higher grade concretes, I need to re-evaluate the beta 1 in order to make these two pictures equal. Up to 30, this 0.85 and this equation 0.85 into C is valid. Now next step is that point of application beta C. Now there is not one as subscript, beta is one factor, multiply with the actual unit axis depth to get the point of application of actual force. If I will make this beta C equal to the Whitney's proposed point of application of the resultant force CC, and I now put A equal to beta 1C, which is actually the beta 1 C up to 30 megapascal, it is equal to 0.85 C. So I just replace this beta 1 with 0.85 C divided by 2, it will give me answer 0.425 C. So I have C on this side, C on this side, so it means what is beta up to concretes of 30 megapascal. If I will use beta equal to 0.425, this will give me the point of application of both pictures equal to each other. So in this way, Whitney proved that use for concretes up to 30 megapascal, A is equal to 0.85 C and beta equal to 0.425, which is half of beta 1. Not only the magnitude but also point of application will be equal. And moreover, for higher grade concretes, this equation can be used to determine the beta 1, which you can review at home, because in my recorded presentation you will find the discussion on next slides. So please watch that video recorded with section.